So today, we're going to talk about something truly groundbreaking. It's a new framework for treating severe brain injury, a strategy that's all about turning hope into a structured, testable plan to help people who are conscious but trapped inside their own bodies.
All right, so to really get this, we first have to understand the profound human challenge they're trying to solve. And honestly, we're talking about one of the most devastating neurological injuries you can possibly imagine.
Just try to imagine this for a second. Your mind is completely there, you're totally aware of everything around you, but you can't move. You can't speak. You're trapped. For these patients, communication might be boiled down to just blinking their eyes.
So this condition has a name. It's called locked-in syndrome. And the core challenge here, the real biological brick wall, is that the adult central nervous system, it just doesn't really know how to repair itself. Because of that, current therapies are mostly supportive. They help patients manage, but they can't actually rebuild those broken neural highways. This new framework is asking, what if we could?
Okay, so this is where the story gets really wild. The initial spark for a solution, it came from, of all places, the biology of cancer. Yeah, you heard that right. The researchers started with this really provocative question. We all know cancer can be incredibly invasive and destructive, but what if we could somehow harness that power for healing? So, the very first idea was this concept of tumor mimicry. They saw how some cancers are aggressive enough to literally invade nerve tissue, and they thought, hey, maybe we can copy those powerful pathological mechanisms. The goal was never to use actual cancer cells, of course not. It was about co-opting their methods to guide nerve regeneration. But as you can probably guess, this kind of pathology hacking came with some massive, massive risks.
And yeah, those risks were just too big. They forced a really crucial pivot. The initial idea, well, clever, was just fundamentally too dangerous, too uncontrollable to ever be used in a person. And that led them to a solution that was so much safer and honestly, way more elegant.
And this table just lays it out perfectly. Look at the tumor mimicry approach. Uncontrollable? Check. High risk of causing cancer? Big check. Feasible anytime soon? Nope. But the new approach, this organic guidance, is the complete opposite. It's structured, you can tune it, and there's no cancer risk. It's something we can actually work on now.
And this really gets to the heart of it. They shift it from trying to mimic a disease to instead emulating health. As the paper puts it, instead of mimicking pathology, the revised framework turns to the body's own constructive blueprint, embryonic development. In other words, they decided to look at how the body builds itself in the first place, using those precise, controlled processes to guide repair.
So what does this new, safer approach actually look like? Well, the researchers used this really great analogy to break it down into 3 parts. It's like a computer system, with hardware, software, and an operating system. And you absolutely need all 3 parts working together. You've got the hardware, which is a physical scaffold to guide nerve growth. Then the software, which is the intense neurorehab to make it all work. And finally, the operating system, a quantum optimizer that personalizes and pulls it all together. Let's start with the hardware. Think of it like a biodegradable trellis for your neurons. It's acellular, meaning no living cells are implanted, which is a huge safety feature. It has these tiny microchannels to physically guide the new nerve fibers where they need to go. It even releases a timed dose of growth factors. And get this, it has a repellent fence to stop nerves from wandering off in the wrong direction. And the best part? After a few weeks, it just dissolves, leaving only the new connections behind. It's totally safe by design. But, that amazing hardware is completely useless on its own. That's where the software comes in. This is all about intensive rehab based on that classic neuroscience principle, cells that fire together, wire together. You need high repetition training to make those new connections strong and functional. They even boost this with things like non-invasive brain stimulation to get the brain ready to learn, and functional electrical stimulation to give feedback to the muscles. It's like teaching the brain how to use its new wiring. Okay, so this all sounds amazing, right? But it brings up a huge, huge problem. You've got the scaffold design, the dose of the growth factors, the intensity of the rehab. There are literally millions of variables. So how on earth do you figure out the perfect personalized combination for each patient while making absolutely sure it's safe?
Well, that's where the operating system steps in. And this is the quantum computing part. The whole massive problem is translated into a format called QUBO,
Now, you don't need to be a physicist to get this. Just know that QUBO is a type of problem that quantum annealers, a special kind of quantum computer, are just built to solve. They can search through a mind-boggling number of possibilities and find the single best answer.
So here's the workflow, and it's actually pretty straightforward. First, you input everything, all the treatment parameters, and, this is key, all the safety rules. Then you run that QUBO model on the quantum annealer. And what it spits out is the one treatment protocol that's not just optimal, but is also guaranteed to be safe. So how does it enforce that safety? This is so clever. Hard limits, like the maximum dose of a growth factor you see here, are literally programmed into the algorithm as huge penalties. Any potential solution that breaks one of these rules becomes so mathematically expensive that the quantum annealer just ignores it. It's not a suggestion. Safety is literally built into the physics of the calculation.
Okay, so we have this incredibly sophisticated three-part system. The question now is, what's the actual plan to get this out of the lab and to the patients who need it?
Well, a roadmap is, very wisely, a cautious one. It's broken down into phases. Right now, they're in the preclinical stage, testing everything in rodent models to make sure it's safe and it works. The next step, in the near future, would be a small human pilot study, maybe 10 to 15 patients, focused only on safety. And way down the line, only if the current approach isn't enough, they might explore more complex ideas.
And it's really important to be clear-eyed about the challenges here. This isn't a sure thing. For one, what works in rodents doesn't always work in humans. There's also a small theoretical risk that you could create some bad, non-functional connections. And honestly, just getting regulatory approval for something this complex, a combination of a device, a biologic, and software, is a monumental task all on its own.
But in the end, this really brings us back to the core message of the whole project. This framework doesn't promise a miracle. It's not a magic bullet. What it does offer is something much more valuable: a structured, testable strategy. It's a pragmatic, safety-first plan. It's a credible ladder that could, one day, help people climb back to autonomy.
You know, it's an incredibly bold vision, tying together bioengineering, neuroscience, and even quantum computing. And it leaves us with this powerful, lingering question about the future of medicine. Can we truly engineer a ladder back to autonomy for those trapped inside their own minds?